Hello again. This is another clip for my Year 10 class who are doing triple science. Looking at physics today, chapter 10.2, weight and terminal velocity. And in this chapter, we are going to look at the differences between the mass and the weight of an object. Having said that, we're also going to be looking at the motion of falling objects acted on only by gravity. And then we're going to move on to what we're going to look at is terminal velocity. Now, when we look at terminal velocity, we need to also understand the fact that there is a resultant force that is basically made up of the weight and the air resistance. But first of all, let's just take a look at what mass and weight actually is. Now, a lot of students basically do confuse this matter because when we look at mass is just a quantity of matter that an object contains, and it's this mass that stays constant regardless of the fact that whether it's in a gravitational field or in space as well. So it's important to understand that that the mass is going to be constant in any volume of space, whether it's going to be a gravitational field or it's going to be space. Now, this mass experiences a gravitational force. But when a gravitational force is acted on a mass, then we are now talking about the weight of the object. And the weight of the object is purely dictated by looking at the mass times by the gravity. So when we now look at, say, for example, this section of the book here, we are looking at, my apologies, we're looking at the weight, and the weight we can see from here is that weight of an object is a force acting on it due to gravity. Now, the weight is a force, a vector quantity, because the weight is measured in magnitude and it also has a direction. So when we now look at the mass of an object, the mass is going to be constant, but when we talk about weight of an object, the weight is always going to be directed downwards and towards the center of the earth. Now, the mass of an object depends on the quantity of matter in it, and the mass is measured in kilograms. Every object that you can see around you is going to have a mass. At the same time, every object that experiences a gravitational field, a gravitational force, is also going to experience a weight. So, if we now look at an example here where we have 1 kg mass, in approximation, we could say that 1 kilogram is 10 newtons. But then, having said that, a 5 kg mass is going to be then obviously then 5 times by the gravitational value, which is going to be 10 newtons acting per every kg, and therefore we have a force of 15 newtons acting on the object. Now, as you can see down below here, we have got an exact value here, and the exact value is 9.8 newtons acting per kilogram, which means that every 1 kilogram of mass experiences a force of 9.8 newtons. So therefore, if you have an object, let's say the mass of the object is, let's say, 1,000 kilograms, then we can say that 1,000 times by 9.8 will give you a weight, a force acting due to gravity of 9,800 newtons. What's interesting is that an object that basically weighs 9,800 newtons, or whichever weight the object of a certain mass has, when we take it into space where there's going to be gravitational value is going to be 0, then we can say that the weight of the object is going to be 0, and therefore there's no force acting on the object. And this is our understanding at GCSE level. It's important to understand that we're looking at purely assuming a gravitational value is going to be 0 in space. Now, as we go down the page here, this really formalizes what we are talking about here, where the weight is going to be equal to the mass times by the gravitational field strength, which is G, and we can see the units are going to be in newtons, kilogram, and therefore newtons per kilogram. So what that means is that if you had a calculation where the mass of the object was in grams, okay, it's very important to understand that we need to change the grams into kilograms before we multiply it out with the gravitational field strength, which is 9.8 newtons. And which will obviously give you the weight of the object. So just to reflect on what we just said right now, if we now basically go back to what we just looked at, it's important then to understand or summarize what we said is that the mass of an object is just purely the quantity of matter in it, which is basically measured in kilograms. The metric unit is kilograms, and therefore what that means is that the mass is going to be constant if you take it anywhere in the universe. Now, however, the weight is purely dependent on the gravitational pull due to gravity, which means that as the mass gets larger, for a certain gravitational field strength, let's say on our planet is 9.81, the mass is then multiplied by 9.8 or 9.81 newtons per kilogram, which will give you the weight of the object. Now, for those of you who are more interested in understanding a little bit more about the gravitational field strength, the gravitational field strength is not going to be 9.81 newtons per kilogram anywhere in the universe. It all depends, for example, where you are. Let's say, for example, if you take the same mass, let's say on another planet, could be Jupiter, okay, or it could be, let's say, Neptune, okay, or what we need to understand here is that the gravitational field strength on Jupiter is going to be a lot larger, which obviously means that when we multiply the mass of an object times by the gravitational field strength, which could be a lot larger in the case of Jupiter, then the force experienced by the mass is going to be a lot larger as well. Therefore, the weight is going to be a lot larger. Say, for example, if it was possible, let's say for us to stand on, or if it's possible for us to actually be on Jupiter, okay, therefore we will experience a lot more weight acting on us. Okay, that's all for now. Next time, basically, I will move on to looking at terminal velocity, what terminal velocity means. Any questions, please leave some feedback on my YouTube clip, and obviously I'll see you really soon. Many thanks, bye.